Is there a secret alpha longevity in development?
How much is this idea worth? Nothing, right? What is important is, who's going to, spend the millions of dollars, years of work that are going to be required to take that all the way.
Welcome to Learning With Lowell. Today we are joined with Javier Tordable. He's the technical director at Google. Normally I ask everyone to subscribe to tell the Google gods that this is content worth watching, but I assume since we have Javier here that they're listening and they'll know on their own. So Javier, welcome to the show. I look forward to jumping into these topics.
Thank you very much. Thank you, Lowell. Yeah, I'm very happy to be here and I'm very excited about chatting with you.
You started out in mathematics, and then you slowly worked your way into being in Google. And as someone who does MVPs and works on projects, I always am curious when people have an idea and they're mapping it out to see if it's real, just for fun. You seem like a guy who just tinkers a little bit. Maybe I'm wrong. But do you have an ideal tech stack or like a go-to way to test out your ideas when you have ideas to play with? It could be personally or professionally.
Yeah. I mean, I don't know if my idea for a tech stack is better or worse than anybody else's. I would say what matters is
a quick note. Uncle Sam wants you to help make this show successful. Subscribe and become a member today.
To be able to try out something as quickly as possible or with as little cost as possible. And this is something that took me quite a few years to learn. I think when, there's this phase, right, when you're learning programming in which at the beginning, everything may be very simple and you just, start your Python command line and start typing things and see what happens, and then things get gradually more complicated, and then you suddenly need to set up your continuous integration and your code repository and your access policies for data buckets and so on and so forth, and then eventually things kind of get a little bit simpler again. So I would say today when I need to try something out, I would probably use Colab. I really like Colab. It's very easy to get started. It's very easy to share things with other people. It's easy to get a GPU, for example, if you need some kind of hardware acceleration to try out models or whatnot. And especially there's a lot of collabs that people have put together. So when I need to do something, like say I need to try out LLM, or I don't want to play with a new API, I'll probably start with a collab, and then if it works, or if I need something a little bit complicated, I'll figure out how that code needs to be deployed or whatnot. But I like Colab, and if for whatever reason Colab doesn't work, there's like Vertex notebooks, which is basically the same thing but inside of somebody else's Google Cloud project.
Yeah, and this relates to a topic I wanted to ask someone who works at Google and can answer this. What is the benefit in doing Google Cloud versus on-prem if I'm building something? Is there? I imagine if I'm sitting and I'm thinking I'm in longevity, I'm trying to build up an MVP, maybe a mathematical model, maybe something with an AI for computational biology or what have you. I would probably go to a Google Cloud for the computation versus spend the money to build on-prem. But I am curious if you're building like doing some R&D or building an MVP, how do you see the Google Cloud or the cloud in general on-prem debate that happens?
Yeah, so I would say there are two sets of reasons. One set are the classical reasons why somebody would move to the cloud as opposed to working on an on-prem system, and the other set, it's a little bit more, what are the reasons right now to do that? So when you look at the evolution of cloud, right? If we had this conversation, 4 or 5 years ago, the reasons to use cloud would have been basically the following. You can reduce costs, for example, because when you set up a system on-prem, you have to put up all the money first, you have to build that system, and then you pay for that, whether you use it or not. So if the usage that you make of that system is sporadic, for example, maybe you use it only for 3-4 hours a day, every day, well, you're still paying for the whole thing instead of paying for what you use. So when you move to the cloud, you switch to a cost model, which you pay only for what you use. And that sometimes is very meaningful. If you're doing experiments, for example, that is significant difference between running your experiment on a computer on-prem and waiting 3 days for it to finish, versus running it on, say, 100 machines in the cloud and waiting just half an hour for it to finish. And then, maybe doing another experiment. The cost may be very similar, but doing an experiment in half an hour means that you can do multiple experiments in a day and move much faster than if you need to wait a week before the iteration of your experiment. So a lot of the reasons why people moved to the cloud initially were, reduce costs, to consolidate, different architectures and so on and so forth. Now, today, I think most of the reasons why a company or an organization moves to the cloud are related to accessing capabilities that are much harder to access in on-prem systems. So, in Google Cloud, for example, we have this system called BigQuery, which is like a database, but much more powerful, and it has a lot of functionality that most databases just don't have, right? Where you can process, geodata, where you can, run AI models as part of, your SQL queries, right? And it has a lot of really cool functionality. So, that functionality in general is not going to be accessible if you run on-prem systems. I would say it's maybe the same with some AI systems, right? So if you want to use large number of GPU accelerators, if you want to use TPU accelerators in order to drastically optimize your machine learning code, that capability is only going to be available in the cloud. So, so the classical reasons which were related to cost, have now become reasons related to functionality, right? The cloud, ours or somebody else's, typically have things that are just not available with on-prem systems.
And I think at the recent, I don't know if they're called shareholder meetings, it's just like where Google gets together and talks about their products. The Sundar, if I'm saying the name right, I've never said it out.
Yeah.
Sundar, thank you. It was more on AI products, like the Gecko, I think it is, like the really small one that can like be on phones or like modular devices. I feel it seems like Google is going more towards AI technology, in their systems versus where they used to be like an indexing and search function type company. It seems like that's like the transition they're going. And so I was wondering who are the leaders in AI, and then from your point of view, is a closed system, which I think Google is more of a closed system. Then there's like false open AI, which is not a open system anymore, or like Microsoft, which is like junior Microsoft, versus like these open LLM type models and AI that's being developed with everyone working together. Where do you think the advancements for people who are listening in, wondering about longevity or wondering about AI, where do you think like the biggest advancements are going to be coming from? Is it going to be like Google, who's now transitioning more and more towards AI, Microsoft, who's like buying up OpenAI's weights and whatnot, or is it going to be a system that is open where people can just like clone the repo and then build whatever they want off of it?
Yeah. So lots of things there. So let me try to unpack.
Yeah.
So Google has actually been focusing on AI for a long time. Google has been an AI company, I would say, for many years, and the amount of investment that Google has made on AI research has been, staggering. Literally hundreds, if not thousands, of people working for many years, and billions of dollars, right? And a lot of it has been made public, right? Transformers, for example, right, which are one of the core fundamental technologies behind large language models were invented at Google, right? A lot of that was published. A lot of the original LLMs, better than T5, right? Were published by Google, and they served as the basis for a lot of other developments later. So, in general, Google has believed in open source and releasing scientific discoveries in the open for a long time. Google is not the only company that does that. I would say, in many ways has been leading the field, right? But there are definitely a lot of other companies that have followed that path, and now we find ourselves in a situation where there is really strong economic incentives in large language models. These systems or these models turn out to be really useful for a lot of things, and I think a lot of people are feeling, or a lot of folks within large companies are feeling that there's going to be a very strong economic incentive. So obviously there are many people that are working on that. Now there's this funny situation where because there are these really strong economic incentives. Many people are competing from the open source side of the world with the large companies, and I think it's really hard to say whether the best LLMs are going to come from the Google and OpenAI of the world, or they are going to come from the open source side of the world. I think the jury is still out on it. So back to the world of maybe longevity or scientific research, I would say what matters is it's not so much who has built better technology. What matters is how can somebody take that technology and use it for their specific use case in the cheapest or easiest way possible. And sometimes that would be leveraging some product that somebody has put together, and even if that product has a certain cost, right? But makes it cheaper or faster to get to the respective result. And sometimes it would be leveraging open source technology. So if an organization is really strictly limited in their budget, there may not be a choice, outside of applying for grants and trying to run things in whatever cloud or whatever on-prem system is necessary is available. But if there's a budget, right, and that can be compared versus the amount of time that it will take to get results, sometimes it's better to just pay for something that is going to be easier to use. So I don't think there's a single size fits all answer to this, right? I think it's something that needs to be considered in the whole context of what are the goals of that organization, where are the budget of the resources.
Yeah, and I think that you've been a fellow at the Longevity Fellowship Retreat. There's a third word there, but I don't remember what it is. But so when people have come up to you and they say they want to do something with a computational AI or just AI, machine learning, LLMs, whatever, for the pattern recognition benefit of it, for whatever they want to do you recommend them go into the Google thing? And if I'm like pushing to the edge of what you're allowed to say about your employers, let me know and I'll pivot. But like, do you recommend them a certain aspect of what Google can do, or is there something out there that I mean, granted, like even within that more focused use case, like there's subdivisions of that use case where you would like suggest different products, but what are the different options for technology that you generally have pointed people to when you have helped them as a counselor?
Yeah, so for people that, again, like people that have no money, I would say Colab is really hard to beat. Colab is something that is basically was originally developed by Google Research and is mostly free. Even the paid version is very, very cheap compared with the value that people get out of it. So I think it makes a lot of sense to experiment with. If it happens to be a startup, for example, that has some budget, I would say it may be better to opt for another solution, something that brings a little bit more of enterprise flavor and security controls and all sorts of things that are important for companies that may not be as important for, say, research institutions that are operating in the open. But it's not a solution for everything, right? I would say sometimes you see other cloud providers that they come and they give grants and they give lots of money to people, and maybe Google doesn't match that or whatever. Well, then that's what makes sense, right? So if you're a research lab and somebody from Microsoft comes in and says, "Hey, we'll give you $100,000 for this," if you run it on our cloud. I mean, it's kind of hard to argue with that, right? And again, I don't think there's a single solution for everything. There are a few things that I like that I think Google Cloud product is really, really good, better in many ways. But I think the BigQuery and data analytics solutions are really good. I think the AI infrastructure is pretty good and improving very, very fast. So the whole serverless infrastructure, right? How we deploy containers and how we run them, on demand, right? I think that story is pretty good as well. The hardware accelerators for AI, story is also really good. Other things, maybe not so much, right? But again, it depends on the peculiarities of the specific organization. I would say for people that come from the research side, that they just they compile some data, they want to start to understand it, see what can get out of it. It's really hard to be something like Colab in terms of price and what you get for very little money.
Yeah, sounds like a good option if you're trying to do like a proof of concept, to see if what you're having even has legs. I think sometimes people, when they're building something, especially if they're new to it, they tend to try to get like the fanciest, most expensive version of it. And if you can find, free or free credits or, cheap, and then migrate up as you go, that's pretty good. And it sounds like Collab is not, I haven't used it personally, but it sounds like something that you can just migrate up and use other systems as your needs grow, which is good.
Yeah. I mean, it's basically a document, right? A notebook in which you have Python code, and it has the capability of running that Python code in a computer in the cloud. And there's a version of it that is completely free. You basically get those resources without having to pay anything. And then the paid version, I think, is like $10 a month, right? It's literally, it's super cheap. And the good thing is that there's already a lot of notebooks that people have created and have shared. So you could go and say, well, let's imagine that you have an idea for using a diffusion model in order to generate, synthetic data for, say, cell images, right? Well, you could try to run that locally, right? But many of us don't have heavy workstations with GPUs and so on and so forth, right? So something like Colab would probably be very easy. Like you could go and try to copy a stable diffusion Colab from somebody else and start making changes and upload your data to it and process it to that model, and all that would be basically free, right?
When you're trying to learn more about computational modeling, I've recently discovered a website called Hugging Face, and I like people do so much on there. It's pretty cool. Do you go to that, or is there like a different resource, water and hole, that you go to learn more about the potential of AI and how use cases and stuff like that?
Yeah, well, I mean, Hugging Face is great. I personally, to be honest, I get a lot of my AI news from Twitter. Just kind of funny, that pretty much everybody that is doing interesting research in AI goes and then posts their findings or the callouts or whatever, or their Hugging Face reposts on Twitter. So I get most of my research from there. But when you mean modeling, right, there are many different types of modeling, right? So the kinds of things that I've been spending a little bit more time lately are in the computational chemistry side of things, which is a little bit of a different universe. But for AI, I mean, Hugging Face, I think it's a really nice resource. I personally don't use it that much. I just don't have time to go through everything, but I think it's super useful.
Yeah, I didn't know if there was somewhere on Hugging Face, if there was like an AlphaFold open source Hugging Face equivalent of something like that for people to pull and then do some stuff off of it. But it doesn't sound like something that you use. So if anyone's out there looking to learn more about this type of field, it sounds like Twitter and search. And also the cool thing about Twitter, if you do the search thing and then you click the advanced option, you can get more granular. Like the base search sucks, which is interesting because then we're talking to a person at Google, and we can talk about search, which is where they started. So what I was recently listening to this interview with a guy named George Hotz, Hotz, who is the founder of Tiny Corp, and he worked at Facebook. I think he was a Twitter intern for a little he was an intern at Twitter for a little bit when he's trying to solve things. I said that backwards. But and he said that he said that Facebook and Twitter are alive, SpaceX is alive, but that he considers places like Google to be dead organizations that they don't innovate to the same level as these other ones do. And I was curious about the dichotomy of what that meant. But as someone who lives in Google and gets to see, like, you get to be at the coalface for all these things, well, I guess, does that make sense? Like, is Google like his proposition basically was Google's not going to be a dominant player in like 5-ish years. Like it's like all these other people are going to come up and like eat the market share. Bing's going to be like, he thinks that Bing's going to be a search engine that people will use. Which now that with LLMs and stuff, I actually like, I kind of like Bing a little bit better. Bard is okay. I use ChatGPT the most, but all of them are not like truthy system, which is kind of bothering me. Like it's like they're pattern recognition systems for what is most likely the outcome versus like what is. Think of like cite their sources that make me happy, which is just an aside. But as someone who's at the coalface, what does it look like? Is Google going to be not dead in 5 years, but in the sense of like relegated to a lesser standard? Like they're kind of like at the pinnacle now.
Yeah, I would. I don't agree with that statement, right? And I would strongly question that. I would say innovation takes many forms, right? Yeah, and you could say that startups in some way innovate very fast because somebody can go from an idea to publishing somebody in a code, publishing something in a code repo and then posting about it on Twitter, right? And be able to push, code to production within hours or days, right? And that's great. That's one measure of innovation, right? Whereas larger companies in general are subject to certain sets of constraints that smaller companies are not. But larger companies also have vast amounts of resources that they can dedicate to solving problems, right? So Google, from the beginning, still now, is an organization with a very, very strong innovation culture. If you there was actually a chart that, of course, I can't show because we're not presenting. I don't have it handy. But if you actually look at the number of publications in top AI journals, peer-reviewed journals, Google by itself is, or at least was the last time I checked, the top organization in the world. Well, like Google publishes more in AI than anybody else combined, including, in many cases, top universities in the world, right? The combination of Google plus DeepMind, I would say, has been the leader in AI publications for many years, and I think it still is now. It's kind of hard to say that Google is not a nobody place, right? All that stuff is actually happening and is being validated by the scientific community. On the other hand, I also understand that sometimes when organizations grow to a certain level, it's much harder to innovate. And you could also say, well, how come Microsoft seems to be moving so fast now? Well, they signed a deal with a much smaller, nimbler organization, and then they took those products and incorporated into their own products, right? Which, in some way, that is also a way to innovate, right? But it wasn't a Microsoft engineer that created the ChatGPT models, right? They took them and they integrated into their own products. So, I would say every time that somebody says something like that, kind of reminds me of this quote. I don't remember who it was. But it was something like reports from my death have been greatly exaggerated, right? I would say large organizations have a lot of inertia, right? And they go through ups and downs. But it's rare to see an organization that is fast moving and innovating and suddenly become less relevant.
Yeah. The number one search in the world is Google. The second level, I can't think of the word. I don't know what's wrong with my brain today, but is YouTube. So like the two biggest places to index information and access it are within Google's library. Apparently the biggest one for younger people is TikTok. Like they do the most searching on TikTok. Though the information is not that great. Like when I try and research certain things on TikTok to get like bite-sized versions of it, it's not the best. And there's a lot of dancing people, which I don't find research worthy. But so I can see it both ways. But at the same time, Bing now is slightly more useful. I went from like, wow, Bing sucks. Why does this exist? You guys should just close this down. So now
let me add a couple of things. So I'm not a TikTok fan, right? I personally think so I barely if ever watch TV, right? I think it's a very useless thing to. And with TV, I mean just whatever's playing on TV, right? As opposed to watching a specific movie or a series, right? For some reason. And I think TikTok kind of falls into that, right? So it can be
Yeah.
very, very entertaining, right? But the the amount of information that you get, or what you learn, or what you can develop as a person by watching TikTok for a few hours is basically zero, right? As
Mhm.
opposed to going to YouTube and watching TED Talks, for example, right? Or as opposed to going to Google and searching for some information and reading Wikipedia pages, right? So I think it's it's a great time waster, and in that sense, they have made a product that fulfills those requirements, right? But it's not something that I would say is interesting. So the second thing that you mentioned, right, is now Bing is more useful now that they have ChatGPT attached to it. That is true, actually, and that is one positive thing for Google, as it is. Who would have guessed that having a search engine would actually help with your large language model, right? So if you watch the Google I/O conference a month ago, or 6 weeks ago, something like that, one of the interesting things is how the combination of large language models plus traditional search can create a product that is better than any of those two separately. And I think that's probably the future of search. It's probably going to be something that combines the capabilities of abstract understanding of extracting information, of really capturing user intent from LLMs with vast repository of information and a well curated database from a traditional search engine. So the combination of both things is probably the future of search, rather than one or the other.
Mm-hmm. Yeah, it'll be interesting. The next 5 years, I think OpenAI was like the fastest company to $1 billion in history, which is pretty cool. I just like things are really accelerating, which I think what?
To $1 billion what?
I think it's $1 billion. Like they made like $1 billion. I think in like the quickest amount of time. I think that's what I was reading.
I don't think so. I think
just like
so. Yeah, if I remember right, they were very fast in getting to 100 million total users. So that was super quick. I think.
Oh, maybe it was just users.
Yeah, but I'm not sure they're making $1 billion just from the APIs, because they charge $10 a month for access to GPT-4, I believe, right? And then of course I have the API, but I'm not sure if they have disclosed their revenue numbers. Maybe. I don't work for them. I don't have any insider knowledge, right? But I don't remember seeing them disclose their revenue.
I don't know where I read that, so I can't cite my source. If I'm wrong out there, people leave in the comments, and I will debate you once I reread that. So, talking about comments, I asked people for feedback or thoughts on what they would want to talk about, and I'm not gonna say this person's full name because I don't want to dox them, but I'm gonna say Simon out there. Thanks for writing in. They say, I wonder if there's a path for computational chemistry and AI research to go beyond small molecule design. If so, what could be done? I thought that'd be a fun first fan listener question to start with, because people. Anyways, yeah, take it away.
Yeah, like we could spend half an hour talking about just this. This is something that I'm very, very excited about. I think I'm not a computational chemist, right? But I've been following the field for a few years and learning a little bit about it. And I would say there is a tremendous promise in using AI and other computational techniques to improve computational chemistry. Not just small molecules, but also different types of macromolecules. I would say the most obvious example, right, that hopefully many of us, I imagine many people watching this podcast would know about, is AlphaFold, right? AlphaFold was at least to me, but I think to a lot of people, very, very inspirational. It was kind of a milestone, because it was a landmark moment in applying AI to something that is useful for biology and for research and for our understanding of the world. Of course, AlphaFold operates on proteins, right? And many of them are very big. AlphaFold itself has its limitations in terms of the size of the protein, but there are other models that people have built from from AlphaFold, ColabFold, and so on and so forth that kind of overcome many of those limitations. And folks have taken the same principle or the same principles that that, that that provide the foundation for how AlphaFold works and applied it to other types of molecules. I think there was a startup last year that was trying to create 3D structures of RNA molecules. But RNA in some ways, has a lot of interesting peculiarities, right? From a conceptual perspective, we may think of it as just a sequence, right? But RNA also folds in really interesting ways, right? And it may interact with other proteins or with other things inside of the cell in ways that we don't yet fully understand. This company was trying to build AI models that predict the folding of RNA molecules. There's a lot that we still don't understand about DNA, for example, and how it wraps and unwraps around histones and what structures it takes when it's inside of nucleus and when it's transcribed, right, and what kinds of things enhance or promote or stop its transcription. So I think there's a lot of room for applying similar techniques to other components, and of course I think the holy grail in some ways for all of this would be to be able to model entire organelles and entire cells at some point. I think that's still a little bit too far away. Technology will need to advance significantly. Computational power will need to increase drastically for us to be able to step that. But I would not discard that something like that may be possible in the future.
Why is it that with AlphaFold, AlphaGo, and all these other different little branches of the technology, why aren't they able to just replicate it and then apply it to all these different areas and just like gobble it up? Instead of allowing there to be competitors, why don't they just like have another team work on the RNA thing or other different molecules, since they have like a proven model for alpha folding it, versus just letting other teams or what other groups do that if they have like all the money and stuff behind it as well? What prevents them?
I wouldn't say there's something necessarily preventing it, right? But at the same time, I would question that there is a model for it, right? So AlphaFold as a machine learning model leverages data sets that were compiled over many years. These are in the protein data bank, and it leverages the fact that proteins evolve with certain structures. So protein folding is a really complex problem, right? Proteins can be composed of hundreds or thousands of amino acids that fold in all sorts of different ways. So the number of potential variations in which they can fold is very, very large. In the order of the number of atoms in the universe. These things are there's a tremendous number of possibilities. But the reason why AlphaFold and similar systems work is because proteins don't just fold in random ways. Proteins fold in ways that have evolved to have a certain function. So if you have a certain sequence in two proteins, you may have similarities in how those two proteins fold. Even if you have a different sequence across two proteins, if those proteins say may have a similar function in the cell, they may have evolved to have a shape that is related. So in some ways, there is a latent space or a manifold of potential structures of proteins, and AlphaFold helps us find within that space. Now, if you go and take another potential molecular simulation problem, that space of that manifold of possibilities may or may not exist. So, for example, in the case of DNA and RNA, there's just a lot less structures available in the PDB. So we could go and try to train a model that tries to replicate the same things that AlphaFold does, but that may or may not work as well, right? Or if you think in terms of, say, other types of molecules or interactions between different types of molecules, the data available may be different, right? Or the internal structure of that problem may be different. So I don't think it's true that there is a model that works on this and can be applied across a lot of different domains, right? I would say, in general, each one of these different problems may require a specific approach, right? We're still at a phase in development of technology where we don't have a magic wand, a general AI that we can apply to these kinds of things, right? We're still having to tackle each problem in a bit of an independent way, depending on the peculiarities of that problem.
Is there a secret alpha longevity in development? Is there like any secret projects like that?
Not that I know of. So Google has been, folks at Google have actually been interested in longevity for a long time. And of course, that's why Alphabet started Calico many years ago. And there was some interesting research that came out of that, for example, on partial reprogramming. I think, some of the people that worked on AlphaFold then went on and started another subsidiary. It's called Isomorphic Labs. And I don't think they have shared much about what they're working, but they're obviously working on things related to biology and applying AI to biology. So whether they're translating to therapeutics, for example, or new computational tools for finding new drugs, I think it's still to be seen, but I think that would be very interesting. One good thing that Google has is, for a long time, Google has attracted a certain type of person, right? That is unafraid of asking hard questions, right? One of those questions is, what can we do to extend lifespan? So, there's a surprisingly large number of people at Google that I think are interested in this type of questions, more so than in the population at large.
Yeah. So there could be something going on, and you can't comment. Is how I'm taking that. So the this in silico model we just talked about a minute ago to be making like virtual cells or what have you, which reminds me of a question that a listener asked, which is, their name is Paraphyllis. I doubt that's her real name, so I'm going to say it. They said this week a biotech company in silico medicine started human trials of a drug discovered and designed entirely through AI. Given that Demis Sabas at Google has said his dream is to create a virtual cell, and he thinks it can be done within the next 5 to 10 years, which is, we're going from like proteins to like a whole cell, like we just mentioned. Coupled with the explosion of AI technology in the next 5 to 10 years, if we couple a bunch of couples here with AGI technology with simulated biology, will it be practical to cure all diseases with all these different things seeming to explode at the same time? Is the question of Paraphyllis 075. In your opinion?
There are a lot of assumptions in that question. So first of all, I think the work that in silico therapeutics is doing is great, and Alex Chabranco has been a really strong proponent of longevity for a long time. So kudos to him and his team for embarking into clinical trials for this drug. I think when they say that the drug was designed entirely through AI, I think that is, in contrast with a more traditional method in which medicinal chemists would look at things and tweak things back and forth, right? So they have a platform that can do a lot of those things in an automated way, which I think is great. But we're still a little bit far away from a system that can look at phenotypic information about a disease, for example, and come up with a drug that may be effective for that, right? So something like that, still a little bit far away. I can't really talk much about what Demis Hassabis is working on or not working on. I'm not close to him. He doesn't share what he's working on with me, so I can only speculate. Same as anybody else. But I would say, in general, AI is advancing really, really fast. And a lot of the techniques that are built for general AI systems will be useful for biology in many different ways. Like they will be useful for computational biology, say understanding genomic or multiomic data, and in particular in relation to health and disease. And I think that would be useful for suggesting new therapies or new potential targets for specific diseases. Computational chemistry is advancing also drastically. One of the things that has been very interesting is how folks within computational chemistry have been using graph neural networks, for example, or geometric neural networks using, let's say, equivariant models, and people have been able to build, say, machine learning models for docking that work just as well as many traditional heuristics. People have been building force fields for molecular dynamic simulations using machine learning. Many of them have got orders of magnitude faster over just a few years and approaching a level of accuracy and ability to scale up that is compatible with traditional force fields. And molecular dynamics is kind of one of the workhorses of molecular simulation. So I think, if many of those trends continue, it stands to reason that these AI techniques will be very, very useful for a wide variety of simulation tasks. Now, having said that, there are a lot of things that we just don't know how to do, right? So when somebody goes and says, well, will AI be able to cure all diseases? That is a very complex and nuanced question, right? There are many diseases for which we have no good therapy for, right? There are genetic diseases, for example, caused by mutations, where we may be able to come up with therapeutics, for example, but a genetic disease may be related to the relationship between different genes in particular ways, right? And we have no, they may be so rare that we have no way to figure out, how those different mutations relate to create the disease, right? There are infectious diseases, for example, that are caused by bacteria that evolve or mutate in many different ways that make them immune to a lot of antibiotics, right? So when we came up with a new antibiotic, that doesn't mean that bacteria is not going to continue evolving, right? So we don't have drugs that change over time, for example, right? Like once a drug is approved, that's the molecule, right? That's the compound that is given to people. That doesn't change every month, right? Which is it's a very interesting question, right? In a world of software, we're used to things that are shipped all the time, right? But when a drug is approved, that same drug is the one that is given to people for the next 20 years, right? That the drug, that therapy doesn't change. And there are a lot of diseases in which we just don't have good targets, right? I think in many ways, a lot of the diseases of aging are problematic because we don't have a deep enough understanding of it. We don't know what the good targets for it are. Alzheimer's, I think, is a great case. For the longest time, we thought that accumulation of amyloid, beta amyloids was the reason for it, right? And people develop all sorts of immunotherapies and ways to kind of remove those amyloid aggregates. And it turned out that may have been a little bit of a red herring, right? Like that is involved in the development of the disease, but even if we were able to remove them completely, that didn't solve the disease, right? So if we don't have a deep enough understanding of a disease to even know what the targets are, there's very little that an AI system, even a fantastic AI system that could come up with the right molecule to inhibit a specific target, right? Even if we had that, we wouldn't be able to use it to tackle diseases for which we still don't understand what those targets are. So, the way that I think of it is not from the perspective of, how could we build this amazing system that will solve every problem, right? I think about it from the perspective of, let's try to find the low-hanging fruit first and solve that problem, and then move on to the next one. Right? In computer science, we have this concept of greedy algorithms, right? Which I think is really useful, right? That you find an action that takes you towards a local minimum, and then you continue moving in that through that local minimum, taking actions that are optimal at each step. And for certain kinds of problems, that algorithm takes you to the right global solution. So I think that is a useful way to think about aging. There is so much about aging that we just don't know. But if we could solve one part of it, and then another part of it, and then another part of it, it stands to reason that we could make progress in the overall goal. So, for example, right, like one approach regarding aging that I like very much is the approach that ovary and the sense, formerly of the Sense Foundation push that the main causes of aging are damage, right? So if we could go and repair the damage and restore the system to the state previous to the damage, then we could alleviate, many of the diseases, of many of the consequences of aging. So if you can isolate that damage and repair it in each step, then eventually you will find out, say, other internal reasons that are not damaged, or you could, trigger, or make sure that overall system lasts for longer, right? And I think this is a very interesting approach that a lot of startups within longevity, for example, are exploring. I really like the work that Repair Bio, for example, is doing with their enzyme that breaks down oxidized cholesterol, right? Underdog also is they're not called Underdog anymore, right? This is Matthew.
Cyclaridia, Cyclarity, yeah.
So they're doing, they're trying to tackle that same target through a different approach, right? I think that approach makes a lot of sense, right? That is, a product that accumulates, it causes damage. If you could go and remove it, all other things being equal, it stands to reason that are really beneficial, right? And I think there are a lot of other areas where that same approach can be applied for aging.
Mm-hmm. It does. It sounds like one big issue is not so much the AI technology on the side to do the analysis of what's there. It's that we don't have a lot there to understand what could potentially be there. Like we don't have like these deep data lakes or this long-term biomarkers of humans. Like I've always felt that as an opportunity for entrepreneurship that I'd buy up or start building out like a blood drive center and just slowly, and then have like a little checkbox and you get like an extra like $5 or a coupon. And then you let all your biomarkers be, go to a database for all this research that would exist. And I just keep doing that because blood drives are actually really profitable businesses. But it does seem that huge limiting factor is we don't have a central repo or a huge data lake that people can pull from and to have a make larger models from. It does seem like it's kind of like in the old days when we're trying to understand the human brain, we only really understood it through the damage. Phineas Gage got a railroad spike through his head. It's like, oh well, that part of the brain kind of regulates some important things, and it seems like we're kind of in a high-tech version of that where we're seeing the damage and assuming, oh, we patch that up, we can fix that part of the brain, they won't have that problem anymore, and then going in that direction. So I wish there was a way other than just making a giant blood drive and then have an extra box to get an extra coupon. If anyone out there does that, please send me a coupon. But I won't trademark it.
I think you had the Mark Hamalayan in the show, I think, back, and he talked a little bit about that, right? I think it's interesting that we don't have, say, public government organizations collecting all the data. There are efforts that are ongoing. For example, I think for the brain, right? I'm familiar with the Allen Institute here in Seattle that is been doing really interesting work in human brain, but unfortunately, there's nobody collecting the data necessary for doing something like this, specifically in the context of aging. Yeah, so that is a big gap.
Yeah. You can just license it out. I feel like you make money for this. And someone needs to do this, so I don't have to do this. It's essentially my logic. I like telling people my ideas. I don't know if you do this. I like telling people my ideas, and if they do it, then I don't have to do it. It's like it's a win-win. I'll just go focus on something else that no one else is focusing on. Because like sometimes people are like kind of like little bat people, and they don't like telling people their ideas because they think people are going to steal them. Not that you are a bad person in any way, but like there's a layer where people don't share ideas because they're afraid people steal them. Versus like they're working out the IP and stuff, which makes sense.
I think ideas are really not worth that much.
Yeah.
Right? And any interesting idea probably has occurred to many other people at the same time. Like, some of these things are not truly novel, right? Even in the context of startups or companies trying to do things, so many ideas, they look interesting on the side and people have made money out of them, right? But what really is valuable is being able to execute on those ideas. I think it's the same in longevity. There's so many ideas about potential experiments that we could do things that would be useful to learn more about the mechanisms of aging or diseases, potential therapies that could be explored. But the tricky part is actually making that happen, right? So you could go and say, well, rapamycin, for example, is an interesting drug. It seems to, work. The mechanisms that it affects are conservatory species. That's the reason that it may be useful to protect against aging damage in humans, right? So you could go and say, well, why doesn't somebody come up with a better molecule similar to rapamycin, but patented? Or something that is patentable, and then go and do clinical trials and then make millions out of it. I mean, is that a good idea or a bad idea? I don't know. I think it's probably a good idea, right? Like, the reason people are not, and some people are, I guess, working on it, right? But I would say the idea itself is worth nothing, right? Anybody that has to spend, a year, a couple of years in longevity, come up with a whole bunch of different ideas. The problem is that executing on this idea costs millions of dollars and takes years of work, right? You could say the same thing about senolytics, right? Kind of, talk a little bit about the dasatinib and quercetin and the experiment that was done at the Mayo Clinic in mice and so on. Well, all that's great, right? None of these, drugs are under patent protection anymore, if I remember right. So, like, the interesting thing would be, could somebody find a senolytic or a combination of senolytics that targets senescent cells better, and then do a clinical trial and prove that that is useful for a variety of for other diseases in humans? Sure, right? How much is this idea worth? Nothing, right? What is important is, who's going to, spend the millions of dollars and years of work that are going to be required to take that all the way from an idea to an actual therapeutic. I think in longevity, people in general have been very open, sharing the kinds of things that they are working on. Which doesn't mean that the ideas are not valuable, but what it means is that the real value comes from executing on those ideas.
I was recently listening to a podcast with Matt Angle, who's the founder of Paradromics, which is a competitor to Neuralink. Though, Matt, if you're listening, I'm not a fan of your technology, but I still think it's a good one. But in terms of architecture, I think it's just a little antiquated compared to what Neuralink's doing. But he talked about how the brain-computer interface phase state, like the industry, is one where like people are very open, like longevity, but they're right at the moment where like everything used to be like Intel in the old days, but then everyone broke apart from Intel and started building their own chip companies and doing their own thing, and then they were more quiet in that time period, and then they reaggregated up. And it seems like longevity's in that phase where there's not, like, they're in a phase of openness because there's not there's a lot to go around. There's like more things can be done by working together, and then eventually there'll be a phase where like people go back to being quiet and being closed off. It seems is what is happening now in BCI technology, and I imagine will help in longevity as well at some point when a critical mass of people are there, which I don't think is there yet. I think there's a lot of interest, but I don't think there's enough people working in it and dedicating their lives to it to the point where there is that watershed moment. I don't know many industries. At a certain point, industry just starts closing off and building up walls and saying you can't come in, and working with IP and stuff like that, which is sad. But then if you just have a beer with them, they'll tell you the things. They don't talk about them in public, which is kind of sad. But yeah.
Yeah, I mean, there's also some industries, I think, have people that are more driven towards or that are more mission driven than driven purely by profit, right? So one thing that I really enjoy, for example, is in the AI field, like, people publish their results openly, right? There's a tradition and there's a culture of publishing results, and I think that has been massively positive, right? It's part of the reason why AI moves so incredibly fast, because people are building on top of each other. That doesn't happen in pharma in general. So I think it would be great if longevity follows in that tradition, in the sense that, or follows that pattern, and people can build on top of each other and iterate faster, rather than protect every single idea in the hope that there may be some economic value out of it. And I think an interesting thing in the world of longevity right now is that people that are in it tend to be more mission driven. than people in other industries, which is great. And I think, in some ways, uh, it's crazy that there aren't more people championing it, right? Like, I think, maybe there's still a lot of people out there, right, that are not as conscious about their own mortality, right? So I think the folks within the longevity field have realized that at the end of the day, we're all in the same boat, right? We're all human, and unless we do something about it, we'll have a very limited amount of time in this planet. So,
Mhm.
great if we can all work together to start solving that.
Yeah, collaboration is key, especially at this phase of it. I imagine when there's more VCs and more MBAs in the equation that just look at things as like little bean counters, then they'll start ruining the pot for everybody and slow things down, which sucks. But maybe at the same time, we can like rehabilitate them like wounded koalas on the side of the road. So longevity fellowship, we mentioned this a couple of times. You're a counselor there. What is the special sauce that you bring to the table? You have such a diverse background. You started in mathematics, which I think is like I'm quoted for saying numbers are delicious. I think they're fun to play with. Like, how often when you're working on an equation or working on a problem is like the solution to the problem in the problem that you're working on? I kind of like that simplicity. Maybe on your level, maybe there's no solutions, but like on the one, like calculus and stuff, like you just look at it long enough and you work on it and like eventually work out the problem. But when you go in to help people, what is the thing that you bring that they seem to need the most help with?
So I would say a couple of things, and my journey, I think, has been a little bit different than most of the people that are interested in longevity, right? In the sense that I don't come from a biology background, right? So I come from a tech background, and I have, my professional experience has been in building software, right? So I would say a couple of things that are interesting. One of them is that because I come from that background, I had to go through the journey of trying to figure out where I could contribute to the field. So, for people that, again, come from that biology or life sciences background, I think they don't have that problem, right? Somebody who's an MD, right? There are, very clear ways in which they can contribute to longevity, right? Somebody that has a PhD in molecular biology, right? It's very obvious how they can try to figure out different mechanisms and try to, advance their understanding of aging in a specific way. But for folks that come from tech, there are many people who find themselves in this situation. They may have a career where they have made, good money, right? And then maybe, working on interesting stuff, but maybe there's something missing, right? And being able to work on advancing our understanding of longevity and aging, and hopefully at some point be able to contribute to the therapies, a lot of some of those things. That is a path that many of us have to go through, right? And I think I already went through that, so I developed a way of thinking about it and a framework that I think is useful for other people. Second thing is, for me, a lot of that translated into computational chemistry. And, I would say, I don't know if it's, the area where I could contribute the most or not, right? But, I always tell people, right, is, just like the old saying, when all that you have is a hammer, everything looks like a nail, right? Mm-hmm. So for me, coming from the software side of the world and having working in AI for a while, I have a set of capabilities and a set of tools. So I look for, where can I use those tools? So, I used to tell people, I'm not going to go and put on a white coat and jump on a lab and start doing experiments on mice. There are a million people in the world that could do that better than I can. But the kinds of things that I know how to do are, building software, leveraging AI and other technologies to drive things into information, right? So that's what led me to start learning about computational chemistry and different things that we can do to improve the way that we simulate molecules and simulate biological systems. So when I was participating in the last edition of the camp, I was a counselor. The sessions that I was teaching were about computational chemistry and what kinds of tools can be useful in the very early stages of drug discovery, right? The in silico drug discovery part. Like, how would somebody explore different ideas, try to set up experiments, get results, trying to ideate a little bit, kind of molecules would be useful for certain types of things. Basically, the introductory part of the in silico drug discovery world.
Mm-hmm. The nice thing about helping other people is they get to be kind of like case studies. Like, that's one of the reasons why I don't mind turning other people or giving. Also, it's like I don't know if you've heard the saying, like, give someone $20 and you never hear from them again. Like, it's a pretty good investment. So it's like, I like giving people help, and then if they're like weird about it, it's like, all right, well, I just saved my time. But one of the benefits outside of just the utilitarian, what I just said, is you can see how they go out and take your idea and mold it and use it to inspire them to do something else, which then builds up your own muscle and then the community's muscles and longevity on different ways to execute ideas. And so when you've talked about computational chemistry and you've talked about different ways of executing on using in silico models and using technology to advance that section of the from A to people using it, are there interesting tactics or strategies that people have used or like generated from those conversations that have surprised you?
I think it's still a little bit early. So I haven't seen much in that sense. Yeah, and to be honest, one of the things that was shocking for me when I started spending a little bit more time in the field was how little most of the folks in longevity were using some of this technology. And I think that stems from the fact that they come from purely experimental background. So a lot of the people that are working in longevity right now come from, say, PhDs, for example, or postdocs, where they were doing experiments related to lifespan of animals, right? So a lot of people have experience in yeast and worms and mice and so on and so forth. That's how a big part of the longevity field has evolved, right? Like, you have an idea for some therapy that may make a meaningful difference, right? And then you go and test it in worms, right? That's what for biomedical, for example, that Matt Kaplan is working, right? Like they have all sorts of small molecules that they believe that can extend lifespan, so they go and feed those molecules to worms, and then they go and test it, and they check if the worm lives longer or not, right? Same thing for mice, right? You could go and say, well, I have an idea for this, molecule that can remove senescent cells, and I suspect the mice will live longer, right? So you go and get those, animals and put them in cages and feed them this stuff, and then watch them for 3 years, and eventually you realize, do they live longer or not? It's because so many people come from that background. I think they're not as familiar with the in silico part of drug discovery. I think a few people are familiar with computational biology techniques, so they understand if you have genomic data or other multi-omic data, you can go and do, say, studies where you try to figure out which genes are upregulated or downregulated, as an organism ages, for example, or if you apply certain interventions to that organism, you can figure out, well, how does my proteomic data change, for example, or my transcriptomic data, and so on and so forth. So they understand a little bit of that computational biology side of the world. But if you go a little bit beyond that to the computational chemistry, right? I think most people are not as familiar with it, right? With computational chemistry, I mean the basics of simulating how molecules interact, right? So people would go and they understand, for example, that rapamycin is a molecule that binds to mTORC1 complex, right? But I would say there are very few people who would even know how to simulate that, to take your mTORC1 structure and take your rapamycin structure and generate all a variety of conformations, and then run different docking algorithms or molecular dynamic simulations to try to figure out how that actual binding works, right? And what's the affinity of it, and so on and so forth. Most of those computational techniques are not taught to biologists, right? I think the computational chemistry world has been fairly isolated, specifically, fairly isolated from longevity. So that was one of the things one of the reasons why started delving a little bit into this, right? And in the last edition of the Longevity Biotech Fellowship retreat, that I gave a lesson about computational chemistry, kind of try to open it up the perspective of some of these people to this whole new set of tools that can be used for this research work.
The great thing is the internet, thanks to Google, was part of this. But the world is indexable. You have like all this capacity to learn on the internet. So if they don't have that knowledge base given their background, where would they go online? People listening in who see this as an opportunity, where would they go to learn more about these type of tools and techniques? Is there a spot or a person who's talking about this?
Yeah, I don't know. This is one of the things that I used to joke with people a few years ago when I was kind of getting started in longevity. If you don't come from a computer science background and want to learn a little bit of programming, that's very easy to do. The programming world has become very friendly, very open to newcomers, right? So somebody that studies philosophy can go and spend 8 weeks in a bootcamp learning JavaScript, and then learn how to make dynamic websites and so on and so forth. And then after 8 weeks, they call themselves programmer. And many people like that, find jobs and then develop in technology, right? But imagine doing it, the other way around in biology, right? Imagine taking a computer scientist, putting them on a 2-month bootcamp, doing experimental work on mice, and then after those 2 months, they call themselves a biologist. You'd be like, that makes no sense whatsoever, right? I think part of the problem is that the biology and the longevity world haven't been super open to, I guess, intellectual foreigners in some way. It's really, really hard to learn about these things. So unfortunately, there's no good resource that I can give to people. I mean, there are a lot of textbooks, there are a lot of online courses on specific parts of it, but I don't think there's any good compendium of books or programs that somebody can go through. And I say I'm far from an expert in any of these areas, right? So I think after a few years, I have a little bit of a working knowledge around some of these methods, and I've run them myself, and I know a little bit about how they work, but I'm not an expert, right? So, unfortunately, I don't think there's an easy path.
Mm. Well, they say the best way to learn is to teach. So if you ever want to make like a course or something, I'm happy to sit down and like maybe we can all like crowdsource it together. Because if there's nothing out there, that sounds like a great opportunity to get people involved. Maybe there's like a little course thing we can make or something, and then get Google to fund it. I don't know. Yeah. We can host it on their cloud or something like that.
Computational chemistry 101, right? Yeah, yes. For biologists. Yeah.
We'll call it working knowledge. Working knowledge is not expert. We'll like to be very upfront about it. So, I have like a bunch of rapid fire questions for you, because people asked a lot of questions, and there's like, so just if you don't like the question, or just say pass, okay? Because some of them like they're like a little personal from my point of view, and you'll know when they're mine because I won't cite the person who asked. So the first one is Lunchbox Ultimate, which this person actually asks lots of great questions all the time. But what startups in biology have you personally invested in, and why?
I will say one. So I invested in Prepare Bio, actually, which is working on atherosclerosis and ASH using this enzyme that can break down therapeutic cholesterol. That was, I think, the last investment that I did on longevity. I think it's incredibly exciting technology, and if it works, then it would be also a massive business.
When you invest, do you get a better newsletter of what goes on in the company?
Yes.
Like if I give them like I want to give like everyone $1 so I can get all the good information.
But I can't share, right? And the companies get upset when this stuff comes up.
I just keep it to myself. You do have to label like Lowell you can share and Lowell you can't share, or else like I can share this to someone, which has gotten me in trouble one time, and then now I don't do it to anyone. So what are some books you recommend people check out? Doesn't have to be in the space, or just things that you've read recently that you think people get a kick out of reading.
Oh goodness! I recently read Peter Attia's new book,
Mhm.
And I think it
The Oprah
was
book.
great. You know, probably sorry.
The book that's now on. Oh, he was on Oprah with it.
I don't watch Oprah, so
It came up in the news feed, and I was like, "Oh, that's neat." He got
yeah,
like
I think
it's
it's
like one of those
yeah.
Oprah books that she recommends.
Yeah. You know, it's for anybody that has been on Jedi for a while, right? It's going to be a little bit too basic. But I think it's a great book. I've been actually recommending it to like friends and family and people that are outside of the field. And I think people are enjoying it.
Yeah, I'll have to check it out. I have not read it. The will you ever finish your PhD when you're as you know? In particular, this is my question, by the way. It's a credentialized society. You dropped out, or you didn't drop out. I don't know what the terms are for these things.
I did drop out. Yes.
Okay. Will you get that credential? Will you get that little merit badge so you can put it on the wall? And maybe people are nicer to you. I don't know if they're meaner to you because you don't have a PhD. Will you ever finish your PhD?
It makes no sense for me whatsoever. I actually, you know, I tell people that now, being a PhD dropout, I use it as a badge of honor, right? You know, I think, you know, a lot of people in life are stuck in their ways, right? And they continue doing something regardless of whether it makes sense or not. For me, the fact that I recognized early enough that it didn't make sense to pursue the academic path was something nice. I could have continued another 2-3 years and spend those 3 years of my life for something that would have made very little difference for me. The reason I started is because I really enjoy mathematics and I enjoy the actual work of mathematical research. I thought that was you know, an important part of my life at some point. But you know, my priorities change, right? So I would never finish it.
Mm-hmm. Okay. Is there a weird thing going on? So I haven't taken graduate level courses before in math. Is there something weird in math that you follow that you can synthesize to like a layman? Because like sometimes I wonder. So there's this great movie called Contact, and in it, well, I think it's maybe in the book by Carl Sagan. They say at a certain point when you do pi, like it makes a like a circle of zeros, and I think that's weird or something. I don't know. I'm butchering it. So I was wondering like where is there like some weird magic stuff in math? Because I feel like math is where with the Arthur C. Clarke quote of it's so like so alien, like sometimes it's like not intuitive.
It's
So like is there some like
language, right? You know,
yeah.
if aliens do exist, and you know they should exist, right? If you listen to you know Fermi or whatever, right? The universe is just too big for aliens not to exist. You know, mathematics is a universal language in the sense that it's just ideas, right? So regardless of you know different ways that different intelligences may exist in the universe, the language that they would understand is mathematics. So there's a universal quality out of it. I don't know what the example that you mentioned about, you know, pi, right? But pi is a transcendent number, right? So in general, any sequence of numbers will be present inside of the digit expansion of it, with you know, so you know, if you say, well, you know, is there like a sequence of like, you know, 7, you know, zeros, you know, in pi? That should be, right? This is transcendent. But yeah, I don't know about that example. Like mathematics is full of really interesting facts and paradoxes. So you know, we could spend another hour, you know, talking a lot about that. You know, my favorite was backing out on the name now. Let me actually look it up very quickly so I can tell you the exact name. The Banach-Tarski paradox. So, you know, I'm not going to get into the details, but you know, if somebody's interested, they can look it up. Right? But this is a paradox that comes up in measure theory, right? So you have a ball, you know, like you could imagine a ball, you know, of a certain, you know, diameter or a certain radius. And what this theorem says is that you can take that ball and you can split it into a finite number of pieces, right? So you basically cut it down. It's not really cutting, but you basically cut it down into certain pieces, and then you transform those pieces without changing, you know, the size, without expanding or contracting, right? So you take those pieces and then you move them around. So you rotate them or you translate them. So you cut this sphere into a certain number of pieces, and then you move those pieces around, and then you come up with 2 spheres. Okay. And you can do that in a way that the volume of the first sphere is, whatever you want, one, right? And it's a solid sphere, and then you cut it down, you break down into two pieces, and then you come up with two solid spheres, and each one is of the exact same volume as the original sphere. So you can think, well, how could that be possible? Well, it is actually possible, and you can prove that you can actually do that. That is the Banach-Tarski paradox. Like you can actually prove that there is a sequence of that is a way to divide the points in that original sphere, and there's a sequence of transformations that you can apply to come up with two spheres of the exact same volume as the first one, without again, like expanding or contracting or whatever, like literally just rotating and moving. So I think that's one of the things that really trips people up. It's 100% true.
Yeah, it is weird. I'm gonna have to Google it after this because that does sound odd. But so then, Lunchbox again asks, what conferences, biology conferences, do you recommend people check out?
I really like the ARDD conference in Copenhagen every year. I think that's coming up at the end of August. So that one is a lot of fun. I'm pretty much, a lot of everybody that is doing interesting things in longevity goes to that one.
And
then the longevity biotech fellowship, of course, right?
Yes. Yeah, they got referenced so many times. They should be at the bottom by this point. The BD, weird name. I'm gonna keep you BDs, and you should know who you are. What, if any, collaborations does he do with Alex Zhavoronkovov? Zavaronkov? Yeah.
Well, I personally don't. Yeah, I personally don't work with Insilico. I think they're doing great work, right? I just haven't had the chance to work with them.
Okay, that's the official story. He's not telling us the details. So, what TV? I'm just joking with you. What TV show or movie defines your childhood when you think about it?
TV show or movie that what?
Defines your childhood. When you think about your childhood, is there like a TV show or movie that you'd watch or that you watch and it reminds you of that time in your life?
Not really. Especially not so much in my childhood. I was always more of a video game person than a TV.
Was there a video game?
Yeah, lots. I mean, my favorite video game of all time, not so much in my childhood, but a little bit later, was Mass Effect, the Mass Effect trilogy. It's arguably the best video game trilogy ever made, for a variety of reasons. But I would say, that was very significant for me. But from my childhood, I remember, lots and lots of games that I used to play. GoldenEye on the Nintendo 64. That was. I remember spending hours and hours and hours playing that with friends.
Yeah. Did you ever play Ocarina of Time, the Zelda on 64?
Yes. Oh, yeah. Fantastic game. Yeah, I still remember it, so many years later.
It's my favorite Zelda game, even with all these giant open world ones. There's some just like it's closed, it's small, but there's a lot of dynamism in there. Or like Majora's Mask, that one was weird because it had like time in it, which is kind of odd. Is there a food that you remember from your childhood, or that I feel like food transports people, so I'm just kind of curious.
Not so much for me. I mean, I love Spanish food. Every time I go back to Spain, that's like one of the highlights. Just being able to eat real Spanish food. So I'm partial to Spanish tortilla de patatas, like one of the things that I remember from my childhood.
I've never had that, so I'm gonna have to eat that later.
Like a souffle of eggs and potato and onion. So it's not like Mexican tortilla, right? Like the Spanish tortilla is very different. But yeah, it's a very characteristic of Spanish food.
Yeah, my understanding of Spain is mainly historical, like the Reconquista and other things that happened. So I have to get more into the food side of things. So who is the better CEO, Sundar Pichai or Satya Nadella, in your opinion?
Well, I mean, I would have to say Sundar, right? Like, yeah. I mean, it pays pays my salary, right? So I don't have much of a choice.
Yeah. All right. Then I think that was the last question. There's a few longer ones, but we're running out of time. So I want to thank you so much for being on the show today. when it comes to, you have a website, but it's updated infrequently. Is there a good spot to follow along with what you're working on? Just your excitement for the longevity field?
Yeah, I mean, I would say Twitter or LinkedIn. I'm happy to connect with people in either of those. I try to post on my website every once in a while when I have something a little bit longer than I want to say. But yeah, I would say Twitter is probably the best place. Twitter or LinkedIn are the best places to connect.
Sweet. So we will look forward to the working knowledge of that we mentioned earlier, the course that we're going to make. But all right then, thanks for coming on the show today, and everyone listening. If you got something from this episode, please leave it in the comments.
Thank you, Lowell. Thank you.
A quick note: Uncle Sam wants you to help make this show successful. Subscribe and become a member today.